studies, which are concerned with exactly kind of trying to get a better idea about the dynamic risk of the situation of an autonomous vehicle, and thereby using situation awareness to increase the actually prediction accuracy of these kind of things. So I would like to directly dig into the motivation of why we need that. So if we are putting ourselves into the situation that we are seeing on the slide, where we have an ego vehicle that aims at predicting what the red vehicle in front of this vehicle is possibly doing, then this boils down to the question, so with respect to the safety or collision risk here, will this car brake? And state-of-the-art approaches in this situation are actually taking the current kinematic state of the current situation that can be perceived. So this might be the position, the speed vector, acceleration vector, and also the distance to that vehicle, and uses some simplifying assumptions as to how this situation may evolve. One example here could be to assume a constant acceleration of that vehicle. But if we are reminding ourselves what a human guy or a human driver would do, then we would use much more sophisticated knowledge in order to get an idea what the braking behavior of this vehicle might be. So we would ask ourselves what is going around that red car. Are there other actors influencing this vehicle? Are there traffic rules, and how do they constrain the behavior of this red vehicle? We would also take into account how usually in such situations people behave, and would this be aggressive or non-aggressive, for instance? And last but not least, we would also think about actually the past history of this vehicle. So how did he or she behave like a couple of seconds or even minutes ago, if this was already like in the vicinity of our ego vehicle? And I have to admit that actually this situation here has a little bit been simplified, and actually what this situation looks like is a little bit more diverse. So if we do in a scene update what is really going on, then we can see that we also have like other actors that influence the behavior of this front vehicle. For instance, a side vehicle that is indicating turns to perform a lane change. We have like a yellow traffic light with a stop line associated where the front vehicle for our front vehicle is braking hard. We might also use the information that we are in a rush hour where typically people accept much smaller intervehicular distances, so to say. And we could also use the information that our road surfaces, for instance, a cobblestone, and we have like a wet surface that indicates larger stop distances. And all these kind of things, they somehow influence what we think about the behavior of other actors. So if I would like to summarize that, then we could say that the collision risk, so apart from severity parameters, we are mainly dealing in this presentation here with the prediction of probability. That this risk is highly influenced by behavior likelihood of other actors, but that this behavior likelihood is very highly influenced by situational context. So what is going around our vehicle to be predicted. And if we follow from that what we can do in order to teach our autonomous vehicle to act more human-like when it comes to risk awareness, then what we would do is we would teach this AV to be situation aware, to better predict behavior likelihoods, and in consequence to avoid uncomfortable safety interventions in risky situations by proactively avoiding these situations in the first place, and not waiting until they are there and then do like a full brake that might be very uncomfortable for the ego passengers. And this is what the situation-aware dynamic risk assessment approach, in short, SINADRA, is about. Let's now look into how this can be mapped into architectural building blocks. What we are seeing here is basically commonly known safety envelope architecture, where we are having a nominal driving agent that tries to produce a trajectory based on the knowledge that we have in a world model, and it is the output of a motion planner. And usually, if we are using a secondary safety channel, which then in an ideal case is certified, then we would try to verify this trajectory of the nominal planner and compare it with behaviors that we assume are safe based on certain rules, or usually worst case parameters. And this way we can always assure that we have a safe behavior. And if this certified safety player comes to the conclusion that the nominal trajectory is actually unsafe, then it would be changed in order to be safe, for instance, via transferring into a minimal risk condition or something like this. So this is not what the SINADRA approach is embedded in. Rather, the SINADRA approach acts as an enabler for the nominal driving agent in order to actually proactively avoid situations where the safety player needs to intervene. This is somehow this counter player which acts against the safety player and tries to avoid his intervention, so to say. And how can this be done? We are in particular looking at the situation around the ego vehicle and try to infer, let's say, the likelihood of the behaviors of other vehicles. And we are transforming that in an output into a spatiotemporal risk map that acts as, let's say, a planning space constrainer for our nominal driving agent. So in an ideal case, the nominal driving agent does not know actually why he's then producing a trajectory, because the world model has been constrained in order that these situations that might be safety critical in the end are not reached in the first place. And as I said already, the SINADRA approach basically is part of this green predictive counter player. And the structure on the left side is now used as part of the further presentation in order to explain the building blocks that are within the SINADRA runtime component. And one aspect that is in particular relevant also for this approach is that it is not only operating on the runtime, so to say, that we have this component that can perform this functionality, but due to the fact that we might have very different ODDs to operate in, we might have very different behaviors of the ego vehicle and also of other actors, there is also the need in order to engineer and assure runtime models to, let's say, be ODD specific and enable the SINADRA runtime component to operate based on these models. And I will go now through each of the components of the SINADRA. The first component, if we want to introduce situational awareness, is that we need to somehow get an idea in which situation, or rather situation class, our ego is operating in. And concluding from that, basically what the other perceived actors in the vicinity of the ego, which role they play in the current situation. And as a design time artifact, what we would need to do here is we would need to specify basically so-called situation classes. So this means we are decomposing our situation space into smaller situation classes with the aim to get an idea about the role of other actors for our ego vehicle. You can imagine that this might be very different if I'm having, like, as in the example, a 2-lane following or 3-lane following scenario, so to say, in contrast to situation classes where we have 4-way intersection driving, so which is much more complex, and the roles other vehicles can assume are much different, and the behaviors that are relevant, either critical or uncritical for the ego vehicle, they also differ a lot. And so this component basically answers the question which actors can affect the ego in the current situation class. So here we are seeing, for instance, in this 2-lane situation class that we have a side vehicle and a front vehicle, and we also have like paved pedestrians, and the red arrows here indicate the critical behaviors being relevant for the ego. So this means, for example, that whether the side vehicle is actually, for instance, performing a left lane change or even like keeping lane is not so much relevant for the ego in this current situation, but we would rather tend in the next step to really make sure that we predict correctly the lane change to the right behavior, because it is relevant for the ego vehicle. So this is the basis on which the next step is performed, which is then the behavior intent prediction of these actors that we deem relevant. And here the choice has been to use Bayesian networks for this task, because Bayesian networks are also artificial intelligence models, so they are usually populated with machine learning approaches. But one of the powers of Bayesian networks is that they can be learned with data, but also they have a certain kind of explainability within the structure that humans can comprehend and potentially assess to provide evidences. That is, in my opinion, a huge benefit of BNs opposed to, for instance, deep learning approaches like artificial neural networks as such. So if we are now looking how such a Bayesian network looks like in principle, then we have again the same situation where the ego vehicle has a front vehicle where we want to predict a braking behavior indicated via the output node, where we, for instance, classify between emergency braking behaviors, target braking for a particular stop line, for instance, or following other vehicles, or just cruising around according to the speed limit. And the red Bayesian network here is supposed to contain all the things that we have seen in the first slide, where we are talking about kinematic state of this particular vehicle. But the important step now comes in the next stage, where we are saying, in addition to the kinematic state of the red vehicle, we are also taking into account potential influences from other vehicles, which influence what this red vehicle is actually doing in the next time. So in consequence, we would create additional Bayesian networks that have the aim to predict in the two cases here lane change, and in the front vehicle of our front vehicle, again, using a similar Bayesian network structure for predicting braking behavior and its influence on the red vehicle braking behavior. And last but not least, we are having, let's say, influence factors that we can model that really take into account also these like more high-level features. For instance, we are in a rush hour, and if we know the effect of this consequence, for instance, on accepted gaps, then we could also include this into our causal model and use it beneficially to get an idea about the red vehicle braking behavior. So the result of this step here is that for all of the actors that have been deemed relevant during the first SINADRA step, we are having an idea about the likelihood of the behaviors of those vehicles, which we can then use in order to generate trajectory distributions for these specific behaviors, which is the next step of the SINADRA model. So here, the goal is that we use the behavior intent likelihoods that we have predicted and transform them into trajectory distributions. Why is this relevant? Yeah, this is relevant because a behavior intent as such, it is hard to, let's say, compute something out of intents alone, because one particular behavior intent can in turn be executed in different ways. If we are, for instance, having an emergency braking model, so to say, then it might look very differently if a truck performs an emergency braking via a normal vehicle. And this is then also dependent on capabilities of the particular actors. So that's why we have this step here, where we are coming then to trajectory distributions by employing motion models for the behavior intents of interest and sampling them into trajectory distributions. So this means, like, after this step, for each actor, we are having trajectory distributions on how, for a particular time horizon, the vehicles or actors around us will behave. And if we have this future projection of those behaviors now in the shape of trajectory distributions, then we can make use of existing probabilistic risk assessment frameworks who usually operate on arbitrary trajectory distributions. And the general idea behind this here is that actually these trajectory distributions, that the cumulative overlap of these distributions at particular times are computed. So an overlap means a collision. And this is then basically what is computed into a risk over at a particular time in the future. So, and this is what we are seeing on the right bottom side here. Now we have the situation that we compute these things for each possible behavior intent that we are seeing for a particular actor, and in combination with the planned ego trajectory distribution. And then this means that in this particular case here, we are getting 4 of these graphs. And the idea is to weight actually these 4 graphs based on the likelihood prediction that we did. So in this particular case, the follow vehicle or target brake behavior intent have very low probabilities, and that's why the weighted front vehicle braking risk would then rather tend to assume the shape of the graph of the emergency braking intent risk, so to say. And this is the output that the current component delivers. So it's more like an analytical output at the moment. And in the end, this output can be used in order to generate planning space constraints. So this means like this output can be used in order to create a spatiotemporal risk map, where typical path planning algorithms can then be used in order to find their way through the unrisky space, so to say. And yeah, this was the conceptual part basically of SINADRA. So tool-wise, we implemented that in the past year in the CARLA simulator, where we are providing like at the moment 14 two-lane open scenario files that can be used. And we focused so far on lane change and braking behavior prediction with multiple vehicles. One of the particular features is that since BN inference is not that computationally efficient, and in the worst case, even like NP hard, we kind of parallelize this, as you can assume if we're having more complex situations, that this gets computationally intractable quite soon. And yeah, we uploaded this to GitHub. So anyone who wants to actually have a look into the code or wants to even, I would appreciate that, perform further experiments on that together with me can actually try it out. And yeah, given the time, I would just tend to show you a little the dynamics of such a component. So here we are seeing this in action. So it's really like, as you can see here, a dynamic computation of this risk that we are seeing here. So we are having at the moment this front vehicle that we want to predict the behavior of. And in this simple scenario here, we are having like a slow vehicle in front, which affects kind of the likelihood of the behavior of this guy. And in every time cycle of our computation, we are dynamically picking the Bayesian networks for the respective actors that we are seeing here, and we are performing the inference of the behavior intents also dynamically, and compute this little graph here where we can see right now that actually the closer this is coming here, the closer also the risk is coming here, which we can use to generate like these planning constraints possibly. So this is not like an unforeseeable risk here, so to say, so that here safety intervention would be required, but instead this is an example just for the tool here. Obviously, if we have more sudden events, then we would also have more sudden changes of this risk structure here. Okay, so summarizing my talk, the SINADRA framework mainly does not aim at providing a safety component, but rather aims at predictive safety intervention avoidance, and therefore like improving the performance by proactive avoidance of safety critical situations. So the core innovation of the framework is basically the generation of these composable situation and interaction aware behavior prediction Bayesian networks. And so both the motion models as well as the probabilistic risk assessments, or the last component, these have been implemented according to state-of-the-art approaches that I deem fitting in this case. And yeah, you are all invited to have a look into our open source software realization and providing feedback there. Current and future work is at the moment concerned also with looking at how to train BNs for highway driving, but also for pedestrian behaviors in low-speed IV shuttle use cases, so in semi-structured environments. And one particular point that I'm focusing at the moment is how we can now interface with ego motion planners in order to really affect then also the affect the ego behavior, so to say. And last but not least, I mentioned that in the beginning, the design time evidences are also very important. So if we're creating such a Bayesian network and train it, we also need some kind of evidences at design time about the robustness of this BN. So why is it good in certain situations? And using like the explainability features of the technique as such to potentially also identify systematic weaknesses of these. So in which situations it doesn't perform well, this could then be used in order to, in the next step, do a little bit more worst case reaction to particular outputs of the BN. And with that, I'm through with my talk, and I'm obviously happy to answer questions.